Okay, YouTube fans, this is a project that's been going on for a long time over at my house. At least a year. I started it over a year ago and it's been sitting around ever since. It's about 3/4 done. So there's a lot of the build that's already underway, but there's still a lot to go. I figured I'd show it at this point because it may be of interest to people. What I've done is I've taken my trusty Sherline Mill right here, and it's all crammed up on a little workbench here, so it's not in its final position. But there it is, and what I'm done is I'm configuring it for CNC. So you can buy a CNC kit directly from Sherline along with the mill. They've got packages for that. What I did is I had the mill, I've had this for at least 10 years. I upgraded the motor to the 10,000 RPM motor for the high-speed bits. I haven't quite used it yet for that. And I also bought the motors from a third party. I've got all, let's see if I can get it to the point where you can see all three motors. So the Y motor, X motor, Z motor. The Z motor is probably a little bit overkill for this thing. But you know, they work, they fit. I did buy the Sherline adapter kits for this, and that provides these little conical motor mounts. You have to, and they also replace the feed screws on this. So it's adapted, the feed screws are in. There's not a whole lot of interesting construction to see there. It's basically disassemble it. You have to drill and tap into each of the different slides with a 10 by 32 tap, and that's really not so interesting. So it's pretty straightforward. At some point, if anybody at all watches this video and is interested, I'll be very happy to take it apart and show you how I built it. But the Sherline instructions are absolutely self-explanatory. Another thing I'll say is that back when a year ago when I first started building this, I put limit switches in all over the place. So there are 6 limit switches here which determine the limit of travel of each of the different axes. It's probably overkill for this application. My guess is that whatever I'm CNCing would be small enough that I'd never even get close, but it might prevent a crash. Who knows? In any case, they're there. And now the problem with the limit switches, and they're not wired up yet. They've got the common lead wired up on each one of them, but no others. And the problem is that it presents a lot of wiring. I mean, you know, I'm trying to figure out how best to lay out all of these cables. I've got one cable for each motor, and then I'm going to have 6 individual wires for each of the limit switches, plus a common wire. So there's 7 of these small gauge wires, plus 3 of these larger gauge motor drive wires. And each of these motor drive wires is connected to a harness that comes into the back of the motor. I've wired this according to the manufacturer's spec. There's a couple of ways you can, these are stepper motors. They're not servos, so there's no encoder. This is an open loop system, meaning that you set it up, you index your part, you set your part on here, you figure out where your limits are, the part itself, you put it into the software, and then the machine starts cutting, and you hope that nothing moves or jiggles, or the machine doesn't have a head crash or something like that. And it doesn't keep track of where it is. It knows where it thinks it is, but it doesn't know where it actually is in space. Whereas the servo-controlled CNCs have an encoder in the motor, so as the motor spins, it knows exactly how many times the motor has spun, so it knows where the rotating business end of the mill is. This is open loop. There's no such way to determine other than if you hit a limit. That's the only thing. So I've got steppers. Steppers can be wired any number of different ways, and you need to look at the manufacturer's specs to determine exactly how you're going to wire them up. I believe these are wired in series. I'd have to go back and look. Again, I don't know if anybody's ever going to watch this video, so if you want to know, I will go back and look it up. But there are 6 wires coming out of here, and you wire them in pairs, so you wind up with 3 separate wires. Excuse me, there's 8 wires coming out of here. You wire them in pairs, so you have 4 cables eventually coming out, twisted pair, 1 common, and then 3 individual that drive the individual coils. They go into a connector like so, and this is a standard DB9 connector, and I put that into the motor drive unit itself. So what you have is the stock Sherline Mill. This is their stock mill. It doesn't have any extended axes or anything like that. It's an upgraded motor to drive the spindle, and then I have 3 stepper motors, each of which are connected to their individual drive shafts via these Sherline factory-made connector pieces here. And that's as much as I'll go into there. And again, if there are questions, I'll be happy to take this thing apart and show you all how I put this together. Now let's go into the control box here. So all of this is being controlled by a more or less homebrew control and power system here. And you know, there are as many ways to set up something like this as there are people. And that may be what is confusing about it, and I'll try to go through all the parts that are in here. Maybe I should turn it off first so that we don't accidentally blow something up. All right, what I've got here is a DC power supply. So this is the power supply that's going to run the motors themselves. This is a Meanwell KL35036. Got it from Jameco. It's a 36 volt and it supplies up to 9.7 amps, which for this bad boy, for this little project is way enough. We don't need much more than that for that. So that's the power supply for the motors. I'll get into this in a minute. Then I have 2 smaller power supplies here. These are, let's see if we can see them. If I move these, try to move these out of the way here, and let me see if I can zoom in there to get you in so that we can look. Right, those are 2 Meanwell open frame power supplies. They take 120 volt input, and each one outputs a DC voltage. The top one in this case is outputting 12 volts, and then I just have it stacked on top of a 5 volt supply. The 12 volt supply at the moment, all it's doing is running this fan. Oh, watch out for my hand there, which is not helping you. So all the 12 volt supply is doing is running this fan, which inevitably will cool things down. And the 5 volt supply is running this right here, which is a smooth stepper, Ethernet smooth stepper. And let's see, the power supplies I got from Jameco, they're readily available from just about anywhere. The smooth stepper I got from a company online called Soigeneres, S-O-I-G-E-N-E-R-E-S. I think it's available from a number of different places like internetcnc.com or online CNC. It's a board that's made and designed by a certain group of guys. It's essentially an Atmel FPGA with a bunch of support chips on it. And that enables you to take control from your computer via a what is here. Let's see if we can see that. Let's get that into the picture. There we go. What is here a RJ45 connector. So it's a standard internet Ethernet RJ45 connector that's going off to the computer. And there's configuration that you've got to do for that. I'll get into that in a moment. The smooth stepper has, this particular one has 1, 2, 3, 4 different ports on it. So there's one there, and there's one back here which you can see. So this is port 1, that's port 2 back there. There's one over here in the front, port number 3. It's got a cable on it, and then port number 4 is under these wires here. Now, one thing I've noticed is that if you were to go online and look at the smooth stepper documentation, there is absolutely no help whatsoever to determine what to do with these ports. These standard operational, I think it's 16 or 24 pin ribbon connectors go to it, and the reason there's no documentation on it other than to tell you that they exist is because the function of those ports are programmable, and you program it via your computer software. You don't program it via this board at all. So they're flexible. You can use them for anything you want. In this case, I am using port 1 to drive my motor controller, and I'm using port 3 to drive this thing, which I'll explain in a moment. Okay, and then there's ports 2 and 4, which is port 4 is actually not port 4, it's an expansion port. I guess you can put multiple controllers. I'm only using the one. Okay, so let's just recap. There's a, let's pull out. I got a 36 volt DC power supply here. You can use, by the way, a 24 volt too. It depends on the size of the motors you're using. Again, for this little application, 24 volt, 9 amp, 36 volt, 9 amp is plenty for anything that I can imagine doing with a little Sherline Mill. I've got 2 open frame power supplies here, which are supplying the 5 volt that runs the smooth stepper. Smooth stepper needs 5 volts, about an amp, and that's this lower one. The top one, all it's doing is running the fan, and at some point I might have another 12 volt item in here, but I don't. Now, the motor drive. So I'm using here you can see it's plugged into the back here right there. It's a Gecko Drive G540 multi-axis step drive. You need this to drive the actual motors themselves. The Gecko Drive connects via a ribbon connector, which is here, and that goes to the smooth stepper board port number 1, which I have programmed in my computer software, which I'll show you in a moment. So the smooth stepper board drives is a little 5 volt board. You can't drive the motors from the smooth stepper. The smooth stepper sends commands to the Gecko Drive, which is here, and the Gecko Drive drives the high power from this into the motors, into the Sherline Mill. Like this motor here that's running my Z-axis. So this guy is connected to the Gecko Drive Z-axis, which is down here. Right there. And the Gecko Drive actually has a 4th axis. If you can see that, if you can look at it, you just Google Gecko Drive 540 explains this. And that axis is, if I guess I could put an indexable chuck on the mill and have it rotate if I wanted to. I'm not using that at the moment. All right. So that's the Gecko Drive. This case, by the way, that I'm using, I did get this. I could have made this. This is a metal case that I got online from, I don't remember if it was online CNC or whatever, but it's got pre-drilled holes in it for these things. It's actually made for the Gecko Drive. It's got a nice hole in the back for it. So I didn't have to bother milling anything out and drilling it. I just started plugging things in. It came with a fuse. Let's see if I can get you in there. It came with a fuse holder, a socket for 12 volt IEC connector, and then output of 110 volts there. In the front, I've got my emergency switch, and I've got the on-off. All right, let's just go back inside for a moment. Now, I said I was going to explain this board. So this board I'm connecting to the smooth stepper, and what I'm going to do here is, and it's not hooked up at the moment, I got nothing connected in there except the smooth stepper board. This is a smooth stepper called a smooth stepper LPT board Rev 3. What this does is it's a breakout board, and then for each of the pins in here, there's a breakout, and what you can do is you can tie into this any kind of feedback mechanism you want. So in this case, what I'm going to do is I'm going to tie my limit switches into here, and again, this is all programmable, so depends on what you want to use it for is what these are for. There's no set use. So what I'm going to do is I'm going to tie my all of my limit switches into these here. That'll enable them to talk to the smooth stepper, which in turn is going to talk to the computer software, which I'll show you over here. So what I'm doing here, let's see if we can see that. Yeah, there's not a whole lot of space. I am running Mach on an Apple laptop, which is, I'm actually running Windows version 8 from an Apple laptop, which is running Parallels. So I got Mac OS as the native the native software, and I'm running parallels. And what I'll show you is I'll start that up now. Now, let's see if I can. So I'm going to start Mach. First of all, let me turn on. I'm going to turn on my power supply. I'm going to start up Mach. Mach is running in, again, running on the Windows side. I've had to set up all of my devices accordingly. So in this case, I'm using the Thunderbolt. Let's see if you can see that thing there. Yeah, the Thunderbolt connection for Ethernet, right there. And that is acting as a network to the smooth stepper, which is in the power supply. Excuse me, which is in the cabinet, the control cabinet. So I'm going to say OK. This thing is going to start up. Da-dum, da-dum, da-dum. It's starting, it's fixturing, it's loading. OK, now we got Mach. Now, just for grins, what I'm going to do is I'm going to hit the reset button here. I don't have anything programmed in here. I got no G code or anything. And I'm going to hit the emergency stop on the control box. I'll show you. So I got Mach running here. And let's turn over here. So the control box itself, I'll turn that off for a moment and hit the emergency stop. That enables the drive here on the Sherline. Now, I don't know if you can hear that, but these little motors are buzzing. They're buzzing. And the other thing is I can't turn them right now. See, let me watch what happens if I hit the reset on the power supply. I can turn them. There's no hold current going into this. If I enable the Gecko Drive by hitting the emergency stop on the, or let's say releasing the emergency stop on the control, suddenly I've got some hold current. I can't move that. I could move it. I guess if I could take probably take a set of pliers or something, but that's not movable by me. At least not without breaking it. And if I turn it off, suddenly it moves. So it's got a certain amount of hold current and a hold torque, which prevents it from moving if it tells it it's stopped. And you want it to do that, right? All the axes are in the same mode right now. I can't turn any of these. So the Gecko Drive has basically got these motors in a frozen mode. Now what I'm going to do, just to see how it works, I'm going to come back here to the computer, and I've got hotkeys set up on the computer to move each individual axis. So what I'm going to do here is I'm going to say, all right, move my Z-axis up, and you can hear it's moving. I press the Z key for that. I can press the A key, it goes down. Let me just take you over and you can see it spinning. We're back over there. And let's zoom out. And here we go. I'm going to hit Z, and you see we're going up. I hit A. Oh, get my big head out of the way. Sorry, folks. And Z, we're going up. In fact, if I hit Shift Z, we go up fast. Shift A, I go down fast. I can try the, I think you can see, it's like a Monty Python thing with the head in the way. I think you can see the X. X is moving in the X positive direction. And then I think it's S, moves in the negative direction. Shift, they go faster. All these speeds and feeds are completely programmable in Mach. And let's try the Y. There we go. I got all this junk on the workbench there, so I don't want to get it screwed. I do not have the limit switches set up. But that's the fundamental idea of this. Now, there is a lot of steps, and I went really fast. If anybody's interested, and if anybody watches this, you know, my videos get viewed by one person, which may be me. I'll be very happy to give you some more detail on any of this stuff. Let me quickly explain the software. So I'm using Mach 3. It's a Windows-based software. I'm going to turn all this off so I don't accidentally short something out. There's not a whole lot of room here. It's Windows-based software running on my Mac. All right, it's telling me the smooth stepper has stopped communicating, which is true because it turned it off. Now, what Mach does is it takes G code and turns it into instructions for the motors. Turns it into pulses, which move the motor. So what it does is these pulses, this pulse information, gets converted into network data, let's say. Network data goes to the smooth stepper card, which converts it to commands that the Gecko Drive understands, which in turn sends pulses into the motor. So the Gecko Drive has got some intelligence in it, but it's basically a big amplifier, because you have this little 5-volt thing telling this 36-volt thing what to do, and the Gecko Drive does that conversion for you. So Mach has no G-code creation ability. Mach is used to interpret G-code into motor controls. And there's all kinds of interesting things here. You can set up offsets for different tools. And as I mentioned, it's got the, you can say, ports and setups. So for instance here, I got port number 1 enabled, and as it turns out, all my port 1 connections are going to the motors. I could have easily said, hey, make the stepper port number 2, make it port number 3. The input signals I've set up to be port number 2. That's coming from this board over here. I could have easily set it up any other way. So the problem is when you go look online and you look at the smooth stepper board, it doesn't tell you anything about this, because you're supposed to set it up in Mach or any of the other G-code interpreting programs that are out there. Now, where do you get the G-code from? Well, that's a story that we've got to say to be continued in my case, because I don't have any of that code. You need a CAM, software to take your wireframe models, you know, the 3D image of the thing or the 2D image of the thing, and use that CAM software to generate tool paths and what. And the CAM software is a separate package. It is not Mach, and the CAM software will create G-code that you send to Mach. And then you go, well, how do I create my wireframe models? Well, you're going to create your wireframe models using another tool like you know, the Dassault 3D modeling SolidWorks, or the Autodesk Autodesk programs. So there's 3 steps, and they can get expensive. Now there's freeware online. There's a Linux code that works really well. I've started with Mach on the back end to drive the motors, because it's a known quantity. Now the Mach license that I bought, Mach 3, I think Mach 4 is out by now. I think that cost about 200 bucks. You still have to buy. I still have to acquire some code to generate G-code from wireframe models, and I still have to acquire some code to generate the 3D solid models that the wireframes come from. And you know, that could run into some bucks. So I'm still trying to figure out how to do that. Meanwhile, I've yet to wire up the limit switches. You know, here's one right here. I can't find an elegant way to do it yet, because there's going to be wires all over the place, and I got to figure out how to route them. But I just thought I'd give everybody an idea how, you know, how you go through setting up a CNC like this. There's a lot of instruction online. A lot of it presumes you already know what I just told you. And again, there's many pieces. This is just one way to do it. There are other ways to do it. For instance, I could have used 3 separate motor controllers instead of the G540. G540 is nice, this Gecko Drive G5, because it's got 4 motor controllers in one package. But if I was driving a larger CNC, like on my Grizzly lathe or on my Industrial Hobbies mill, I'd probably have separate motor controllers to drive more current into the thing, because they'd need more oomph. This is just fine for Sherline Mill or a lathe. You can have separate motor controllers. You don't have to use a smooth stepper board. There are other pieces of hardware you can use to do that. I got the smooth stepper because, from what I read, the integration between Mach and the smooth stepper and the Gecko Drive was well known and well worked out. This is just one way to do it. Not necessarily the cheapest way to do it, but it is one way to do it. So hopefully any of that's useful to you. I'm here to help if you've got any questions. My name is Joe, and thanks a lot.